Is it the network or is it the app? That argument can burn a whole afternoon. A packet capture ends it with evidence. In this lesson you'll learn to capture at the right point, filter down to the one conversation that matters, and read the TCP handshake and analysis flags to prove exactly where a network problem lives. When a network complaint reaches Tier 3, it usually turns into an argument. It's the network, no, it's the app. A packet capture settles that with hard evidence. But here's the thing, the real skill isn't capturing, it's reading. It's knowing which handful of packets answer your question and filtering out the thousands that don't. Anyone can hit record, a Tier 3 engineer knows where to look. Where you capture decides what you can conclude. A capture on only the affected client can't tell whether a missing packet was never sent or lost in transit. So capture at both ends, or use a tap or a spam port, and compare. On Windows you can capture with nothing installed using netsh trace, netsh trace start, reproduce the problem, netsh trace stop. And keep it short, 30 seconds of one clean reproduction beats an hour of noise. Wireshark's superpower is its display filters. Start broad and narrow to the single conversation that matters, filter by IP.address and TCP.port. Use TCP.flags.syn to see just the connection starts. Filter on DNS to check name resolution timing. And TCP.analysis.flag surfaces every problem indicator. Then right-click a packet and choose Follow, TCP Stream, to read one conversation from start to finish. Every TCP connection opens with a three-way handshake, SYN, SYN-ACK, ACK. If the SYN goes unanswered, the connection never forms, that's a firewall or a dead server. But if the handshake completes in a couple of milliseconds and then the first data byte takes 4 seconds, the network is fine and the server's think time is the problem. That single distinction, handshake versus time to first byte, resolves most slow app tickets on its own. Wireshark's expert analysis labels the symptoms for you. Retransmissions and repeated duplicate ACKs mean packet loss on the network path. A zero window means the receiver's buffer is full, the receiving application isn't reading fast enough, so that's an app problem, not a network one. Latency with no loss and a healthy window means distance or a slow hop. Each of these patterns routes the ticket to a completely different owner, which is exactly what your RCA needs. Don't eyeball timing, measure it. Use Wireshark's time column and set it to show delta times between packets. Measure the handshake duration explicitly. Measure the gap between the client's request and the server's first response byte, that's your time to first byte. And for a suspected name resolution problem, measure the time between each DNS query and its answer. If resolution takes seconds while the data path is fast, you've just proven the latency lives in DNS. Bring it together into an attribution. Loss patterns, retransmissions and DUP ACKs mean the network path owns the problem. A zero window means the receiving application owns it. A slow first byte after a clean handshake means the server owns it. And slow DNS responses mean the resolver or DNS infrastructure owns it. Your job is to read the capture, pick the pattern, and hand the ticket to the right team with the packets that prove it. Recap. Capture short, scoped, and at the right point, ideally both ends. Filter down to one conversation and read the handshake before the data. Use TCP.analysis.flags to classify loss, flow control stalls, and reordering. Your task: reproduce a slow or failing network operation, capture it under a minute, follow the TCP stream, measure handshake time, time to first byte, and any analysis flags, then write down whether it's loss, a zero window, DNS, or server think time, and which team you'd route it to. Next, log analysis at scale.